everyone. My name is Michaela Saunders. I'm from Ventura College studying physics. My mentor is Paolo Quintos, and my faculty advisor is John Bowers. And this summer we looked at Mach Zehnder interferometer design for optical isolation. So in 2016, what happens in an internet video? 60 seconds. On Google, 2.4 million searches happen. On Netflix, 69,444 hours are watched. On Amazon, $203,569 are made in sales. We have a need for communication, whether it's from person to person to object, or object to object. We need this. And in the future, we will need communication technologies that allow for more data transmission, lower power consumption, and even faster communication, all at the same time. To do this, we can use integrated photonics. We can combine many device functions on a single chip that allow for small size, large volume of production, low cost, and low energy use, all at the same time. Before we start looking at the Mach Zehnder interferometer design, we should understand what an optical isolator is. An optical isolator allows propagation of waves in one direction only. In our case, we are looking for propagation of light in a forward direction and not in a backwards direction. Propagation of light in a backwards direction is caused by reflections, and these back reflections can enter the laser cavity, which can burn out the unit. In this diagram, you can see that this is a schematic of a single mode, two waveguide optical isolator, wherein the matrix there is full transmission in B2 in the forward direction and zeros in the backwards direction for A1, A2, and B1. So there's no transmission in the backwards direction and only in the forwards direction. To make an optical isolator, we need a non-reciprocal material such as Ca. Every material is a reciprocal material, but in order to make it a non-reciprocal material, we need a magneto-optic material in which the magnetic field is applied and changes the environment, making it non-reciprocal. So, and this is a simple schematic of a Mach Zehnder interferometer. The Mach Zehnder works as light propagates in one direction, and at the first Y junction, there is a split, and the light continues to travel in the two waveguides, and then is recombined at the end point. And this is the Mach Zehnder model. So to make our design, we needed to find an equation to describe the light propagating through the Mach Zehnder interferometer. We implement this model into MATLAB, and then engineer the length of two waveguide arms. First, we look at an ideal case, where everything is fabricated correctly, and we find that the length of two waveguide arms should be about 327 microns, L1 and L2. At this case, in 1550 nanometers, we find that there is full transmission of the amplitude, full transmission in the forwards direction, and zero transmission in the backwards direction, thereby stopping the back reflections. However, this is not the case. When we use the same model, but we change the length of the arms from about 327 to 347 microns, we find that at 1550 nanometers, we have some transmission in the forwards direction and lots of transmission in the backwards direction. So what we need truly is a robust design. Isolation at 1550 nanometers with light propagating in one direction only. Because of fabrication inaccuracy, we find a spectral shift. From the ideal case, we see that we would like it to isolation to occur at 1550 nanometers, but truly, because of fabrication errors, it could happen, these kinds of shifts happen. So we need to design a device that will not be as sensitive to these fabrication errors that we find. So in order to optimize for the spectral shift, we take the lengths of L1 and L2 that we found before, and we place them into these equations that can help us find new lengths for L1 and L2, and where N and M are integers of resonance. So what we really need to find is where the minimal shift occurs and what N and M should be. This is a schematic of a waveguide cross-section. We have L1 and L2. We are optimizing for a silicon waveguide based on silica with CIG and SGGG cladding. And first, we look at the width of the silicon and the height of the silicon, where the height is 220 nanometers and the width is 600 nanometers. With these same equations, we find we intentionally cause a shift error of 1 nanometer to see what the lengths of L1 and L2 should be along with these spectral shifts. So first, we find that when N is 0 and M equals 1, we have negative L1 and L2, which cannot exist. So this is not a solution. We see that 0.456 and 0.659 are the smallest spectral shifts for the width and the height, and so N equals -1 and N equals 0 are solutions. We also see that we have the exact same solutions for N equals 0 and M equals 0, and so these two, L1 and L2, are also solutions. So, we have found that in order to optimize, we first must model the MZI for optical isolation using the mathematics and the physics that go along with it. We implemented this model into MATLAB using coding, and we simulated an MZI, and thereby we can design a robust MZI for synthesis. Another question that we could ask in the future is what happens if we change the optical length of these arms? And then we can modify these arms to have a more robust design and possibly use for thermal control. So I would like to thank Paulo Pintas for guiding me along. I really needed it. John Bowers for allowing me to work in his lab with his postdoctoral student, and Wendy Ibsen for accepting me into this program, and UCSB, CSEP, and AIM for hosting us. Thank you.